Hi, guys. I hope everyone's doing well in this crazy time. I wanted to make a short video to kind of review some of the concepts that were in the slideshow this morning and then add to it. For starters, I want to talk about the relationship between energy and work. One of the definitions we have for energy is the ability to do work. So you kind of see this circular relationship here. Energy does work. If you do work, it required energy, and so on. So this is kind of just another principle involved with the conservation of energy as it relates to work. This next diagram that I have here, I'm going to show this starting point right here. A person and a bunch of stones. Now, let's say that this person wants to get the stones up here. In order for them to do that, they have to carry them up this hill. Each one of these stones, let's say, has a mass equal to 1 kilogram. If the height from this point up to here is 10 meters, then we can figure out the change in potential energy for each one of these stones. So at the bottom, the stones don't have any potential energy. This person carries each stone up the hill to this point here, raising them 10 meters. So if we calculate the change in potential energy for each stone, we get mgh, mass times gravity times height. So 1 kilogram times 9.8 meters per second squared times 10 meters. And the potential energy change for each stone is 98 joules. We have 6 stones in the picture. So 6 times 98 gives us a total potential energy at the top of 588 joules. Now, if this person decides to take the stones and drop them off the edge of the cliff, then we know that the potential energy is going to transform into kinetic energy as the stone falls down, losing height but gaining velocity. Now, what if I put a geared wheel in the way of the stone? So each stone that falls is going to hit one of the spokes on the wheel or the gear, causing the gear to move and rotate. Situation, the stone is going to transfer some of its kinetic energy to the wheel, causing the wheel to spin, and the stone will slow down. So by the time the stone gets to the ground over here, it won't have as much kinetic energy as it would have if it did not hit this wheel. Now, what if I attach a belt to this wheel on the inside shaft or axle? So now when the wheel spins, if it spins in this direction, the belt will go that way. On the other end of this belt, I could attach it to another system to do something for me. I could attach it to a sawmill and it could operate a saw, which could cut wood for me. Or maybe it's some type of a hammer system that operates a series of hammers that smash stones into a dust that can be used later on for cement. There's a lot of different options, but the point is this belt can go do some work for us somewhere else. So all these falling stones are basically being converted into energy that's being used to do work somewhere else. But don't forget that initially, this person had to carry each one of these stones up to the hill and then push them off the cliff. So this person had to do work to raise them up to this height. This person had to supply a force that raised each stone that distance. Force times distance is work. This person, obviously, they probably got tired carrying all the stones up to this height. So this person, after doing all this work, was probably hungry and had to replace the energy that they spent, have a sandwich or a meal or whatever. A similar diagram would be a water wheel. In Pawtucket, the Industrial Revolution for the United States happened, where all these mills were put up. They were always put up near rivers or waterfalls, so on, because the flowing water, which has kinetic energy, they would harness that kinetic energy with one of these water wheels. So this water comes down and pushes on one of the spokes here, or the gears, whatever you want to call it, and causes the wheel to turn. So now this rotating wheel, they can add a belt to it or some gear systems, and the spinning wheel can now do work for them. And these water wheels basically operated the mills. At the time, most of the mills were cotton mills. So this was used to operate a cotton press. So one of the big picture or big ideas that come from this kind of setting or scenario is, how did the water get up here to begin with? And this is one of those things where the earth and what happens is kind of a very interesting system. So eventually this water down here is going to just kind of pool into a lake or a pond or something like that. Eventually the sun shines on this water, causing some of it to evaporate into a cloud, which eventually that cloud might move over here to a colder environment, say some mountains. When the cloud gets over here into the mountains where it's cooler, the water vapor condenses and it rains. All of this water then collects in another area and eventually goes down rivers and streams and so on to a waterfall, which then turns a wheel. So the point here is that all the energy originally came from the sun. So as I wrote here, all of the energy originally came from the sun. Again, the sun heats the water evaporates, forms a cloud. The cloud moves to a cooler area where the water vapor condenses and rains. That rain, which collects at a higher location, has potential energy, forms a river that flows and falls down or goes down to a lower area. When it's doing that, the potential energy is being converted to kinetic energy. That kinetic energy turns a wheel, transferring energy to the wheel, causing it to move. And then that motion is harnessed to do work. But again, if we trace whatever work was done by this wheel, if we traced it all the way back to its original point, it would be the sun. Okay, so all energy can be traced back to our sun. What about us? So in this picture, I'm going to apply a force to this block, and I'm going to cause the block to move a certain distance. Force times distance equals work. Because work was done, energy must have been used. The energy came from me. All right. So, because I had to use some energy to do some work, to apply a force, to move this box a certain distance, I've lost energy. I need to replace it. In order to replace it, I do it by eating an orange. So now the obvious question is, where did the orange get its energy? Well, if we just think about it for a minute, oranges come from trees. Trees need nutrients and water from the soil, but most importantly, they need sunlight for photosynthesis, where they take energy from the sun and convert it into some type of a chemical potential energy. And in this case, the sugars that you find inside an orange. But if we go back and we just kind of trace all the energy that is in that orange, it came from the sun. So basically, when I need to replace the energy I needed, and I ate the orange, that energy came from the sun, which in turn, the energy I used to do work to move this block on Earth, that energy ultimately came from the sun.